Hi everyone. Today I'm gonna be discussing Sturm-Liouville problems. Uh, so just to give you an introduction and overview why we are gonna talk about Sturm-Liouville problems. So if you remember, we talked about characteristic equations and characteristic curves in general, or characteristic method, which is one way of solving PDEs, right? Partial differential equations. So another way that we're going to talk about for solving PDEs is separation of variables. This is another method for solving PDEs. Okay, so two techniques for analytically solving partial differential equations. But in separation of variables, what we are gonna do is we are gonna propose a solution which is composed of the product of two functions. Okay, and what we are gonna actually do is we are gonna convert these PDE into ODEs, a PDE into ODEs. Okay, so a PDE, partial differential equation, into ordinary differential equations. Okay, so if you remember, we talked about this before. Ordinary differential equation, in ordinary differential equation, it's only a function of one variable, so only has one independent variable. But PDEs, you can have multiple independent variables like x, y, t. But in ODEs, it's only one. It's going to be only one variable. Either it's x, it's either t or y, just one variable. So we are going to convert it into an ODE, and then we are going to solve ODEs. Okay, and for solving ODEs, we are going to use these Sturm-Liouville problem and techniques. So this Sturm-Liouville problem is going to be used in solving ODEs, ordinary differential equations, which are going to help us in solving PDEs in separation of variables, the second technique that we are going to talk about. Okay, so with this brief introduction of Sturm-Liouville problems, let's get started to define the Sturm-Liouville problems, that what they actually look like. So Sturm-Liouville problems. So Sturm-Liouville problem is a theory of real second order linear ODEs, or ordinary differential equations. Okay, so I'm gonna write a general form of a second order linear ODE. So I'm gonna write it as this: d square u over dx square plus capital Rx times du over dx. So Rx can be a general function of x times the first derivative of u with respect to x plus qx, capital Qx, plus lambda times px times ux equals to 0. So this is a general second order linear ODE, and as you see, u is only a function of x, and this is only a function of one independent variable. So x can be between beta and alpha, and we want to solve this with the following boundary conditions. So in order to give a general boundary condition, I'm going to use a third type boundary condition that we discussed, okay? So we had Dirichlet, which was the first type. We had Newman, which was the second type. And then the third type, which was the combination of two. So I'm going to say at alpha, x equals to alpha, I can write A1 times U alpha plus A2 times du over dx, which is a Newman boundary, at alpha equals to 0. So this is the first boundary condition. And the second boundary condition is at x equals to beta. So this one was here, and the second one is this one. B1 at u at beta plus B2 du over dx at beta equals to 0. So this one corresponds to this, and this one corresponds to this boundary condition. Okay. So this is the problem statement that we have, and we want to now solve this and find a way or technique to solve this second order linear ODE. So I'm gonna define some variables to kind of reduce and simplify this equation into a more common form of Sturm-Liouville problems. So I'm gonna define small rx as e, or exponential, to the power integral of capital Rx dx. This is the first function I'm going to define. The second function I'm going to define is qx, small qx, is capital Qx times Rx. And then the third function, so this is a definition, is px, small p, is capital Px times Rx. So these are the definitions I'm gonna define. I'm defining these three terms, and now I wanna manipulate equation 1, 2, and let's call this one equation 1, to get a simpler form of that and reduce it to a more common form of Sturm-Liouville problem. So what I'm going to do next is multiplying equation 1 by an integrating factor. So we call this integrating factor. Integrating factor Rx. So this is an integrating factor. I'm gonna multiply 1 by this integrating factor, and then I'm gonna reduce it to a more common form of Sturm-Liouville problem. So in order to do so, I'm gonna first calculate the first two terms of this, which are these two. I'm going to see how do they look like. So Rx times the first two terms are d2u over dx squared plus Rx, capital X, R times du over dx. So I'm gonna open these two terms. So the first one is gonna be d2u dx squared Rx, and let me do it down. Oh, oops. So let me do it here. So I'm gonna do it Rx times, well, let's write first d2u over dx squared Rx plus capital Rx times, now instead of Rx, which I have to write, I'm going to write this term. So I'm going to write the integrating factor e to the power Rx, capital R, dx times du over dx, right? So this is just this expression. I just wrote the definition of Rx here. And let's see what it is. So I want you to think of these two terms. Do these two terms remind you of anything? Can you simplify this expression, these two terms, and write it in terms of Rx? So take a moment to think about it. How can you reduce that or write it in terms of Rx? So if you think about it, if you have thought about this, this is just dr, the derivative of r with respect to x, right? We can just calculate it. Just put here e to the integral of Rx dx, and then you're going to get this term. So this is just drx over dx. So now I'm going to write this down as d square u dx square times Rx plus du over dx times dr over dx. So now I want to again think of this. Does this remind you of anything? Can you simplify this expression as well? So if you think about it, this is very simple. From your calculus, if you remember, this we can write it as the derivative with respect to x of this function of rx times du over dx. This is very simple because this is a multiplication, so you will just first, the first term is going to be dr over dx times du over dx, which is this term, and then the derivative plus rx, the function, times the derivative of the second function, which is going to be this, rx times d square u over dx square. Right? So this was just a trick to reduce these two into this. Okay. So the first two terms, if you multiply them, you're going to get this simple form. And now let's go to the second and third term. So if you multiply these by rx, let's see what we'll get. So multiply this by rx. So if you multiply this by rx, from here, we define this small qx. So we are going to get qx. And for this one, I'm going to get px times rx is going to be small px. So you are going to get this one. So I'm just going to write these down where we have them. Okay. And rearrange all the terms. So the multiplication by rx, so I'm going to just write it down. Rx times equation 1 yields to, the first two terms is going to be this one, right? So I'm just going to write it down, d over dx of d over dx of rx du over dx plus the next two terms is going to be small qx plus lambda small px, right? So you're going to have small qx plus lambda small px times ux equals to 0. So this is the more common form of Sturm-Liouville problems. Okay. So this is what you usually see in the literature and also in textbooks. So this is what we call SL problem. So what we have done is we have converted and these second order, general second order linear PDE into this Sturm-Liouville problem by this integrating factor Rx, by multiplying by this integrating factor. Okay. So now I'm going to make some remarks that are important for solving these type of problems. So, remarks. So the first remark is R, Q, and P that appear in SL problem are all functions of X. Okay, so they are all functions of X, not any other variable. The second remark is lambda is a constant. And we are going to say what it is called here. So lambda that appears here is a constant. So the third point that I want to make here is Px is often called the weight function. And sometimes it's shown with Wx as a weight. So the next point that I want to make is multiple lambda values for which the SL problem has non-trivial solutions exist. So we have multiple lambda values for which there is a non-trivial solution for this Sturm-Liouville problem. By non-trivial, we mean like some solutions that are not trivial, like zero or constant. These kind of solutions. So we have lambda values in which we have non-trivial solutions. The next point is finding these lambdas is a part of the given SL problem. So when you have a Sturm-Liouville problem, finding the corresponding lambdas in which we have non-trivial solutions is part of the given problem in Sturm-Liouville type of problems. The next remark is lambda n's, and n I mean the can be any number when they exist are called eigenvalues, and you might have heard this before. So these lambda n's are called, if they are found, and they exist are called eigenvalues. Similarly, solutions corresponding to the lambda n values are called eigenfunctions. So the solutions that correspond to particular like lambda x's or eigenvalues are called eigenfunctions. For example, we can write them as unx. This can be a solution for this Sturm-Liouville problem. And this is the eigenfunction. The next point that I want to make is in Sturm-Liouville problems, eigenvalues, and I'm going to show it with E value from now on, are real. So in Sturm-Liouville problems, these eigenvalues that we are going to find, lambdas, are real. And finally, eigenfunctions, and I'm going to show it with efunc from now on, eigenfunctions form an orthogonal set as this. So the inner product in a function you define orthogonal set by taking their inner product, so that the inner product should be 0. For example, in vectors, if you remember, the inner product, if you have these two vectors, say v1 and v2, then they are orthogonal if v1, their inner product of v1 with v2 is 0, right? So we define something similar for functions, but for functions, the definition is based on integrals, okay? So we define an inner product as of two functions, or e functions, as un and um. And because these eigenfunctions, which are these uns, form an orthogonal set, we say that integral of between alpha and beta of unx, umx, and px, which is just a weight function, right? This is the weight function that we set. P is called weight function, is gonna be 0. Okay, so these eigenfunctions that we are going to find to solve this Sturm-Liouville problem are going to form an orthogonal set in which we have this expression, this formula. The inner product of those functions, eigenfunctions, are going to be 0. And just so you know that this is the way we are taking we define an orthogonal set in the Hilbert space L square norm, and just so you know, I mean, you don't need to know the details, but this is the way we take the inner product of two functions in the Hilbert space with L squared norm. Okay, and so all these eigenfunctions are going to form this relationship, and we are going to investigate this relationship with an example in the next part. So in the next part, I'm going to solve an example of Sturm-Liouville problems, and we will see how we can find lambda or eigenvalues or lambda n's and their corresponding eigenfunctions, and then we are going to show it schematically that these eigenfunctions are going to form an orthogonal set. Okay, so let's have a brief review of what we learned today. So we started with Sturm-Liouville problems. We said that these are necessary step for a separation of variable technique that is for solving PDEs. So in separation of variables, we convert PDE into ODEs, and for ODEs we need to we will use this Sturm-Liouville problem type to solve these ODEs. Okay, and so Sturm-Liouville problem is the theory for real second-order linear ODEs, and we started with a general form of second-order linear ODE, and then reduced it to Sturm-Liouville problem for this form, with this form, by using by multiplying this general second order with this integrating factor Rx, which is just e to the power integral of Rx dx. Okay, so we reduce this into this common form of Sturm-Liouville problem, which is shown here. And then I made some remarks about this Sturm-Liouville problem. So for example, we said that a lambda is a constant, and we can have multiple lambdas in which a non-trivial solution exists, and these lambda n's are called eigenvalues. And finding these lambda values is part of the given Sturm-Liouville problem. And the corresponding lambda values to these corresponding solutions to these lambda values are called eigenfunctions, or u and x. And then we said that eigenfunctions in this Sturm-Liouville form an orthogonal set in which they follow this relation, this expression, in which their integral, if you take the inner product of them, is going to be 0. Okay, so in the next part, I'm gonna solve an example of this, so this point become clearer for you.